Okay, so our first speaker is Boima, and he works on the Handshake project, and this is one of his first talks at a blockchain conference, so be a good talk. Take it away.
Thanks, Ben. Hello, everybody. My name is Boima Fahnbulleh, and for the better part of the last year, I've been contributing to the Handshake protocol. I've literally worked on everything from building the marketing site to writing embedded code for the Ledger Nano S. And if you've ever written a decent amount of C, or worse, had to refactor someone's CSS, you'll know how excited I am to dig my head from under the ground and talk to you all today at this conference. Particularly, I want to talk about authenticated data structures and the path that we took in designing the authenticated data structure that we use for the Handshake protocol. The title of my talk is Urkel Tree, an optimized and cryptographically provable key value store for decentralized naming. Quite long, I know the title is a bit much, but the idea is it's quite simple. The Handshake protocol needed a way to store and query blockchain state in a provable way. We'll get to what type of state in a bit, but this idea of storing and querying blockchain data in a provable way is nothing new. Every blockchain has this idea of a bifurcation between resource-intensive full nodes that store the entire chain state and light clients, which rely on authenticated data structures to reason about the part of the chain state which their operators care about. This idea of simple payment verification, or to generalize like an authenticated state update, was popularized, as we all know, by Bitcoin's use of the binary Merkle tree. Now, warning, there's a basic explanation coming. I'm sure all of you know how Merkle trees work, but I'll include an explanation for completeness of the talk. And for, maybe the people who, for you, right there in front. It's for you. So stated simply, a binary Merkle tree is an authenticated data structure which commits to an ordered set of items. The commitment is made by hashing each item and using those hashes as the leaves of a tree. Then those leaves are pairwise hashed to form the next level of the tree. Basically, you take a pair, you concatenate it, you hash it, and that hash forms the mutual parent of the pair. You continue this operation until you get to the penultimate ancestors, which when hashed together form a root node, which is the commitment to the set. It's called the root hash. Now, to prove inclusion in the set, you start at the leaf in question and you provide the siblings for each successive level up the tree, forming a branch to the root node. A verifier can hash along that branch until they reach the root node and compare it with the root's hash. If it's the same, then it's in the set, and if it's not, then it's not in the set. Now, binary Merkle trees work for Bitcoin because the list of transactions stored in the block is static. Each block gets a new list of transactions. It creates a Merkle tree once, and then it never has to update this tree again. But what if we want a blockchain to commit to data that is updated quite frequently? What if we want to be able to insert data and update data and delete data without reconstructing the entire tree? That takes us to Ethereum. So Ethereum differs from Bitcoin in many ways, but the one most germane to this discussion is that it's not just storing a static list of transactions. It's also concerned with the state of all the smart contracts deployed on the network. These contracts have associated data that are updated frequently. A data structure to fit the use case that Ethereum would need, and now I'm not an Ethereum researcher, but I can imagine that this is what they were thinking when they wanted to figure out this problem, was probably need a key value storage and would allow for updates without having to reconstruct the entire tree every time you update a node. It'd probably want a bounded depth, so an attacker couldn't grind a really long key, put it into the set, and then force nodes to frequently update that key. And then it would need history and independence. History and independence basically meaning that the order in which you update items in the set doesn't depend, or excuse me, the root hash doesn't depend on the order in which you update items in the set. Now, this is important for distributed systems where consistency is hard to maintain. We want to be sure that no matter the order of the nodes, no matter the order in which the nodes make the updates, if they converge on the same set of items, then they will create the same root hash. Okay, another warning, there's another basic explanation coming. For people who know what's going on, I'll get to the good stuff in a little bit. For the people who don't, this is a shout out to you. So we've all seen this crazy diagram of the Patricia Merkle tree, right? And the Merkle Patricia tree, It's actually a variant of the Patricia tree data structure, and it's more akin to a radix tree or like an optimized trie than actually like just a normal trie. So non-optimized tries are key value data stores in which the position of a value is determined by its key. Each node stores an array of pointers to its possible children. And even if there's only one child, and it's obvious where the user should go to find the next node, it still has to store those empty pointers to all those nodes, or excuse me, empty pointers. Instead, what the Ethereum Merkle Patricia tree does is it essentially compresses any node that doesn't have more than one child. So you don't necessarily need to walk down the path from the full length of the key. You can compress nodes that don't diverge and only create a new node once you see a path that needs to diverge. Doing this actually saves a lot of memory because now when you're walking down a path to a key that has a single path that doesn't have a lot of divergences in it, then you don't necessarily need to use a lot of memory to store all those empty pointers to nodes that are useless because you know which node is actually the next one. This is also important because in modern implementations of tries, normally that array of pointers isn't really storing pointers to a memory location. What it's really doing is storing pointers or like a key to a value in an underlying key value store, like level DB. So the optimization that Ethereum uses for the Merkle Patricia tree actually helps with the database lookups as well. Finally, the Merkle part of the name arises from the fact that the nodes aren't really, the key, excuse me, or let's say the pointer to the node, to the next node in the tree, isn't actually a serialization of the node, it's a cryptographic hash of that serialization of a node. So it gives you a bit of cryptographic authentication that you get with the binary Merkle tree, because if you want to change a node in a tree, you have to essentially like reconstruct the whole tree and change the root hash. Or you don't reconstruct the whole tree, excuse me, but you will change the root hash. And so an attacker can't fool you into thinking something's in the tree that's not. So you're probably wondering, why am I talking about all these other trees when the talk is supposed to be about Urkel trees? But as I said before, I wanted to give you a little bit of the thinking on what we were looking at and the different data structures that we looked at to kind of model our light client solution from. So a little background about Handshake. Handshake is a blockchain-based naming system which is compatible with DNS. Its goal is to replace the DNS root zone file and all the root zone servers. The current root zone has been embedded in the blockchain state, and the rest of the root zone's namespace will be issued through open auctions on the blockchain. The idea is that if you can tie the name ownership to ownership of a UTXO and then embed DNS data to the metadata of that coin, then users of the network can query the blockchain state to resolve the name queries, right? But I think it's easy to see that a light client is super important in this type of system. I mean, there are billions of users of the internet, and I would bet that most of them do not care one bit about storing transactions that are clearing on this network. Users of Handshake, it should be so easy as like downloading a small piece of software that doesn't use a lot of memory and updating your DNS settings, or even for those who don't care about much security, like just downloading a Chrome extension that will resolve for you. These users, they don't care about the auctions that are happening on chain. All they want to do is just check out awesome memes and what Joe Carlson's saying on Twitter. So if we think about what our Handshake wish list was, we were really looking for a key value store that had minimal storage. We wanted exceptional performance on SSDs, so consumers' hardware could like could resolve names and make proofs requests. We also wanted a small proof size because DNS records are queried all the time, and you don't want to use a lot of bandwidth trying to resolve names and using the internet, excuse me. And we also wanted that same history independence. Now, when we were looking at candidates for this solution, the last piece about the history independence, it really took a lot of the options away from us. Basically, any rebalancing data structure lacks that inherently, so they all got chopped from the block. So basically, we were down to the Patricia Merkle tree, which is why I was kind of describing it before, and the sparse Merkle tree, which is used in Google's Certificate Transparency project. And now I think it's used in a lot of like Plasma implementations, or at least like Plasma designs. So Originally, we thought the Merkle tree, the Patricia Merkle tree, would be the easy choice. So JJ, our lead developer, re-implemented it and benchmarked it against our needs. However, we found that Ethereum's base 16 trie had like proofs that were too large, and then also the storage requirements were a bit too large for our use case. We also found that the sparse Merkle tree really didn't cut it in terms of performance. So basically, each insertion requires a large number of database lookups without doing heavy caching. And even if you do the optimizations to get around that, there's just way too many rounds of hashing for each insertion. We tested inserting 5,000 leaves at a time, and it required over 1.2 million rounds of hashing and a number of database reinsertions. As a result of this research, we were kind of left thinking, well, what authenticated data structure can we use? They all seem, or at least any of them that are built on current key value storage, and key value storage being like LevelDB and other key value database systems, were just not going to be scalable. So the solution was the Urkel tree. Did I do that? No, I couldn't resist. Sorry, for those of you that get it, whatever. The Urkel tree, which is, as I said before, an optimized and cryptographically provable key value store for decentralized naming. Now, the difference in the Urkel tree is that unlike the Merkle Patricia tree and the sparse Merkle tree, it's intended to be stored in flat files. This removes the overhead of database lookups entirely, making the data structure its own database implementation. So the Urkel tree, as implemented now, stores all of its nodes in append-only files. And we've implemented it using a simple base 2 Merkleized trie. Now, that construction actually shares a lot of similarities with what is called the Merkle set. It's something that was been worked on by Bram Cohen a while back. I think he proposed it as a solution to Bitcoin UTXO commitments. He has a really awesome walkthrough and talk that he did at a Bitcoin SF Devs meetup a while back, so I definitely recommend you check that out if you're interested. And so, like I said, our solution kind of mirrors that construction. So if you look at the structure on disk, unlike the Patricia Merkle tree, we don't have to store 4 different types of nodes. So in that system, you store null nodes, internal nodes, branch nodes, which are the nodes that do the nice compression of nodes that don't have any branches, and then you also store leaf nodes. In our system, we only have to worry about storing internal nodes and leaf nodes, which is great because it's a constant size on disk, and the internal nodes get written to a lot when you're changing things in the tree. Also, because we do append-only files, we can actually expose features that are similar to a transactional database. We get crash consistency if you can store a metadata root on every commitment to some parent database. Basically, for this metadata root, you would just need to store a pointer to the last tree root, and then a pointer to the previous metadata root so you can update, and then a 20-byte checksum. And then when the node boots up, it can walk kind of in reverse from the beginning of the file until it finds the most recent metadata root that has all of the data. So now I want to talk a little bit about the operations that are involved in the Urkel tree. I'll start with insertion. So imagine we started with a root node or an empty root. And then obviously the base case is you just insert a node that we'll call A, which has a prefix of all zeros. And it would now take over the root position. And similarly, if you, there's a mistake. This should be 1100, but for B. But similarly, if you insert a second node which doesn't share a common prefix, then it can just take the second position from the child of the root node. And because there are no divergences below, we can just compress up. Now, there's a fix. Now, inserting C, which is 1101, is where it gets interesting, because now you see that 1101 and 1100 share a 2-bit prefix. So what actually happens, I'll go back, is when we insert C, the way that we handle bit collisions is that we actually store a placeholder node called a null node. And these null nodes are represented in code as just a sentinel hash of zeros. And when we insert that in, the null nodes actually make it a lot easier to prove non-inclusion, and I'll get to why a little later. And then, but now that you see that we have these null nodes here that were grown on the level above B and C, and then the level above that, when we insert another node that fits within those bit prefixes, they fall right into the null nodes, as you see when we enter in D, which has a 100 prefix. You see how it just went down the path to the right of the root node and then fell right in place in the null node that we had constructed earlier. So we don't have to do any changes below that position. And then going from D to adding E, which is a prefix of 1001, grows the tree down further, and the null nodes begin to fill in as well. So now we'll get to removal. And removal may seem a little bit like non-intuitive when like the dead-end nodes are present in the subtree, but basically you just have to ungrow what you just grew. And hopefully the ASCII art like helps out with like the explanation. So if we were to remove the D leaf, which is 1000, from the above tree, we must replace it with a dead-end node. The reason we have to replace it with a dead-end node is because there's still a subtree to the right that doesn't have to get collapsed up, so it's quite simple to just like get rid of it there. But if we want to remove C, it's similar, right? Because B is still its own subtree, and we don't have to collapse the nodes. Where it gets interesting is once we remove B, because as you see, we'll have a whole subtree that basically has only one node, or we'll have a whole subtree that has only one actual node. So what we actually have to do is first remove remove the sibling of B and have it collapse up into its ancestor level as such, right? But as you see, there's still a null node here. So we need to do the same thing and ungrow the tree to one more level. And then again, we continue ungrowing up until there are no more null nodes. And it compresses back to what we had when we only had 2 nodes. And then removing B is trivial because it just takes the place of a null node. A null node takes its place, and then removing A goes back to what we had before. So now I'll go through the proofs, essentially proofs of inclusion and proofs of non-inclusion. Now, it's important to note that our leaf hashes actually commit to the key as well as the hash of the value. And the reason we commit to the key is because if you want to prove non-inclusion, you need to also be able to prove that, let's take an example where you're proving non-inclusion, but there is a node, a leaf in the position that you were trying to prove this leaf doesn't belong, it's just not that leaf, then you also need to commit to the key and the value itself, so you can prove that while there is a node here, it's not the value in which you are trying to attain, if that makes sense. Yeah, sorry, so the 00 is a prefix to let you know that it's a leaf. Oh, do you mean, were you referring to 00 in terms of like the examples too? I'm not sure I understand, but yeah. Oh, I'm sorry. I'm using notation that people may not know. That's not an or, that's a concatenation symbol. I'm sorry. Okay, yeah. Oh, I see what you mean. Yeah, no. It's a concatenation symbol, sorry. Yeah, and so let's say we need to prove the non-inclusion of 1101, which would be C, but it's not C, right? Like it's not the value that is in C, but we want to prove that, basically we want to prove non-inclusion I'm sorry, excuse me, I'm a bit flustered, first talk. Let's say we want to prove non-inclusion of 1110, which is actually not in the tree, right? Basically, all we need to do is prove that we need to provide the hash of the position that it would be in, which is that null node, and then we just provide the siblings going all the way up. It's very similar to like proving inclusion in a binary Merkle tree. We're basically proving that there is a node here that is null, right? And if we want to prove non-inclusion of 0, 1, 0, 0, that's a little bit more tough, right? Because 0, 1, 0, 0 doesn't have any null nodes to rely on. It would move down the tree in the same position of that A node you see right there. So it actually makes the non-inclusion proof a little bit larger because we actually have to provide not only the parent to the subtree that is adjacent to A, but we also need to provide, as I said earlier, the value of A and its key. And so that makes the proof a bit larger, but you don't have to send redundant information because if you provide A, even though it commits to the hash of A, you don't need to like send the hash of A as well because you can just hash it on the client side. So sending those bytes are it's like 32 bytes of redundant data. Now, if we want to prove inclusion of 1100, excuse me, I'll go back. If we want to prove inclusion of C, basically, it's hard to talk about the prefixes in the C. And I'm sorry, it's like a little bit tedious to like go through the operations, but like we have a paper that you can like go in and do it on your own time. But essentially, if you want to prove existence, of 1101, as you can see, you provide the value of C, which is indicated by the brackets, and then the hash of its sibling, and then again, the siblings going up the tree to the root. Now, we did some benchmarking of this tree against the trees that so what happened, we have a JavaScript implementation of the Handshake protocol that binds to C libraries and C++ libraries using Node.js. And we actually re-implemented the sparse Merkle tree and the patricial Merkle tree, and then this variant of our tree, and then ran some benchmarks on high-end consumer-grade software or hardware, And our benchmarks involved committing 50 million leaves or 50 million like names basically, with 300 bytes of like name data. And we did it in 500 leave batches and periodically committed 44,000 leaves to disk. And what we saw was in the 500 value batches, they averaged about like 100 to 150 milliseconds. And the commissions of like 44,000 leaves, after a while, we basically like kept a big write buffer and then like committed to disk every 44,000 leaves. That averaged 400 to 600 milliseconds a piece. And our average node depth was about 27 or 28 bits, which equates to like 800 bytes. And that gives you we saw 1 to 2 milliseconds of proof creation time, which was great for our needs because we really wanted proofs to be super fast to create and verify, and we wanted small proof sizes to save bandwidth time. But the one thing to note, though, on that bit collision, on the 27 bits per key, is that it is possible to essentially grind a key that has a long bit extension. Even right now, Bitcoin block headers can find bit collisions of 72 to 82 bits, or 72 to 80 bits. And so what we actually did was implement a different version of this tree for DOS protection, which is more of a base 2 Merkleized radix tree. So more like the Ethereum-Patricia tree, but instead of being base 16, it's base 2 and binary. It looks a lot like Amari Sachet's Merklix tree, which is why I titled this the Merklix variant, which is also another cool data structure that was also proposed for Bitcoin UTXO commitments, But the problem is it adds a lot of complexity to the code. And so without adding so much performance, it's really just DOS protection. And so we're still actually looking to see which way we want to go, whether we want to use the simple base 2 try, or if we want to use the Merkleized radix try that's more like the Merklix variant. There's actually an open issue on our GitHub, so if you have anything that you want to add to the conversation, please do. But we're still trying to figure out what we're going to do with that. But in summary, I guess the primary advantages that I kind of want to have you take away on from this talk is that using the Urkel tree will give you better performance than other authenticated data structures because we're not using any type of underlying key value store. We're writing straight to disk. That gave us 100x speedups in our benchmarks. Also, there's a simplicity to it in that we're only throwing in two internal types of nodes, or excuse me, two nodes, an internal type of node and then a leaf node. Also, the internal storage of those leaf nodes, as I said, is a constant size, and that helps because those are the nodes that are being, the storage of the internal nodes are a constant size, and that helps because you're always updating the internal nodes when you're doing operations to this tree. And then again, the proof sizes are really small. And also, because we're using cryptographic hashes to commit to the keys in the database, the siblings are 32 bytes, and which that actually is like the reason that the bytes, the proofs are so small, And that's my talk. I'd be remiss if I didn't add that the Handshake blockchain is also in the stage of bootstrapping, and we were looking at a way to have as fair of a distribution as possible, given like that you can't actually like do the Bitcoin thing ever again. People are just gonna try to like come and front run. So we're actually doing this like massive on-chain airdrop that's actually private. We were working with Dan Benet and Riyad Wabi to create a way to essentially, basically we crawled GitHub, pulled SSH keys. Anyone who has above 15 followers and has an SSH key up on GitHub is actually gonna get like I think like 45,000 or 4,500 coins on our blockchain. And you'll be able to redeem these coins without like giving up your anonymity. Basically, it's like a private airdrop. That's really cool. If you want to know more about it, ask me about it later, because I'd love to talk about it, but wasn't in the talk. Thank you.
Great. Let's thank Boima. Also, we have 5 minutes for questions. So anybody has questions?
You mentioned proof size and the time to construct a proof, but I didn't see timing for verification. Do you have any information about that? Actually, I didn't prepare the verification information. I'm sorry. JJ, do you know off the top of your head? It's like a binary Merkle tree. Yeah, I don't have the times, but it's similar to like most authenticated data structures. Well, so the compaction actually right now is like really inefficient, but if you think about like the use case for this database system, really we're talking about like making DNS records, and DNS records become stale. Like after a while, like we force a 1-year renewal, and then when that is renewed, or if like the key is not used to renew and that name like becomes stale in the database, you can basically just like prune that away.
Dan, you had a question? We had one question in the back there.
I'm sorry, scalability as it pertains to the blockchain? I'm sorry, I don't understand. Oh, the tree scalability as the volume of the transactions increase? Oh yeah, that was something that we were actually worried about. So that's why we were so worried about proof size, because like as the amount of leaves grow in the tree, it's gonna get like, it is gonna balloon up, but like having 800 bytes, like basically we benchmarked for 50 million leaves, which is 50 million names. So we hope that that'll keep us below 1 kilobyte for like, the first several years of the protocol. Unless it just blows up and everybody loves Handshake, but which, that would be tight.
All right, thank you very much.
Thank you all for suffering through my first conference talk.